and then you relate that monetary outcome to a set of explanatory variables that are also measured by some some probability sample in a survey. And these are related via this model. So basically, the unit level mixed model links y with x via a set of parameters, regression parameters beta, and also assumes the inclusion of a random effect, which is an area-specific random effect that basically measures what remains unexplained after control between area unexplained variability after controlling for the observed x's and a unit level error term. Okay, so again, you see that with the unit level model, the basic workhorse, as in the case of area level models, is the mixed effects and random effects model. Okay, so under that model, which was proposed by Batiste, Harter, and Fuller, then you can define what is called a BLAP, which basically is a best linear unbiased predictor under this model. And effectively, remember that all model-based theory effectively is based on the same kind of concept. So what you want to calculate effectively, you want to find out about the parameter theta I, that's your population parameter, and you can decompose. You can do that effectively. Here, remember, here we are assuming that the population parameter of interest is a small area average, the small area mean in area I. That's what denotes theta I, is denoted by theta I. So you obviously have data in your sample, which are denoted by Yij. So you could sum the values that you observed in your sample in area I, and then you have another part which we don't observe. So you have all the other Yi's that are not observed. And these are the part that is not observed is denoted by Ri. So that's the unobserved part of in area I, and basically you have these Yij's that are unobserved. Okay, and so what the model is doing here is it gives you a way to assume how these Yij's have been generated, because under the model you assume that the Yij's are generated under the model you assume, and absolutely what you do is basically you replace this second part by predicted values under the model, and that basically will give you a BLAP, a best linear unbiased predictor under the mixed effects model, the unit level mixed effects model that I presented in the previous slide. So for the BLAP, at the moment you assume that sigma squared U and sigma squared epsilon are known. Okay, in reality you will have to estimate those parameters, and then that will take you to the empirical best linear unbiased predictor. You assume that they are known. The other thing that we do in order to simplify a bit the expression is that you assume that the sample size in area I relative to the population size in area I is very small. So normally you will have a very small sample size in a very big area. Okay, and under this simplification, effectively you can express the eBLAP in the way that has been written down here, right? So you write it as summation over the population units of xi beta hat plus gamma I times the difference between yi bar minus xi bar beta hat. And this part here is effectively a random effect, okay? And you can, doing a bit more algebra, you can write that to be equal to x capital bar I beta hat plus ui hat, where x bar I is basically the population means of the covariate. So effectively what you need to assume under this model for estimating the small area mean is that the population averages of the x's are available also in as part of your data. So what the way that this method is working, the unit level model is working for estimating small area means, is that you need to have a unit level survey data set that you use in order to estimate your preferred model, to fit your preferred model. And then for the purpose of prediction, for the purpose of predicting the small area means in each of the areas, what additional information you have to have is basically information about the population averages in area I of the explanatory variables. Okay, and obviously you combine that with the estimates of the model parameters. A few more observations here. The BLAP, as you will see here, as the way we have written the BLAP here, and Angela kind of mentioned that in her at some point as part of session 1, you see that the BLAP is expressed as a combination that receives weight. So this here is a regression estimator, and then the second bit is a synthetic estimator. Okay, a survey regression estimator and a synthetic estimator with weights equal to gamma I and 1 minus gamma I. And under the unit level model, the gamma I, what we defined in the previous session as the shrinkage factor, is having a slightly different form, is basically the ratio between the between area variability divided by the between area variability plus the within area variability divided by Ni, where Ni is the sample size. Okay, if your X capital I, so if your population values of the means of Xi's are equal to this sample means, then the estimator will have the same form as the Fay-Harriot model. If Ni is small, okay, then gamma I will tend to 0, and the BLAP will for that area will tend to the synthetic estimator because the sample size is small. You tend to give less weight to the survey regression estimator and more weight to the synthetic estimator. And if sigma squared U is large compared to sigma squared epsilon over Ni, the BLAP will tend to the regression to the survey regression estimator. Okay, obviously, as we said, for out of sample units, you cannot predict a random effect. So the only thing you can do there is to get your theta hat i's by using the synthetic part, which is basically xi bar times beta hat. There is no way to calculate to predict the random effect for out of sample areas, purely because you see here that you cannot compute these residuals. Basically, you don't have the yi bars effectively here because you don't observe data from out of sample areas. Okay, as with the previous the area level model, you need to estimate in reality the variance component. So you need to get estimates of sigma squared E and sigma squared U, and there are different methods that have been proposed in the literature and in the original paper by Baptiste, Harter, and Fuller. Different ways of using its maximum likelihood or restricted maximum likelihood, but at the end of the day, you effectively the estimator, the EBLAP, the empirical best linear unbiased predictor, will have the same form as the BLAP, with the only difference basically is that here now you will replace in the gamma I, that will be a gamma I hat, where that is replaced by the estimated values of the variance components. Okay. So, but the idea remains the same. Okay, so as with the area level model, obviously point estimation is not such a big issue. It's a very big issue, of course, in small area estimation, but it can be done as we described before. We have an estimator of the small area mean. What becomes even a bigger issue is how do you get a measure of the uncertainty around the estimate. And as with the area level models, there are both analytical and computer intensive methods to do that. And for simple measures, for simple statistics like a small area means and so on, there are analytical estimators that are working very well. Okay, so the analytical estimator, MSE estimator that is the most popular in the literature is, as in the case of the area level model, is the Prasad Rao one, and again that goes back to the paper, a paper by Prasad and Rao in 1990. But we have seen that before. Under that framework, you assume normality for the random effect and the unit level error terms, and the estimator, an estimator of the mean squared error of the EBP of theta hat I EBP comprises three parts: this Z1 term, Z2 term, and this Z3 term. And you see that this depends on sigma hat, where effectively sigma hat comprises of the two variance components in the simplest case of this two-level model. Now, obviously, the naive estimator will include only the G1 and the G2, but you want also to capture the uncertainty introduced by the fact that that the variance components are estimated. And below, I have given you here expressions for the G1, G2, and G3. And the expression for G3 is more complicated, and it depends on variances and covariances that I have not given you formulae for because they're quite long formulae, but you can find the expressions in the paper by Prasad and Rao. The good news is that this estimator has been programmed in various packages, including the SAE package and the EMDI package, and so you can use those packages to calculate the analytical mean squared error estimator. Okay. So exactly the same. It's exactly the same idea as the idea that we presented for area level model. So you get an analytical estimator of the mean squared error, and that's very handy and very good because we don't have to rely on computer intensive methods. The theory is clear, and it works quite well under the assumption of normality. And there are alternative mean squared error estimators that have been proposed in the literature, but for the purposes of this work, this estimator will work perfectly well. Now, if you wanted to consider a bootstrap type estimator, as I said in the previous session under area level models, you can use one method that has been used a lot in the past is the idea of parametric bootstrap. That's not the only way of doing it. There are non-parametric bootstrap methods as well. Parametric bootstraps are quite popular, but obviously they assume that the model that you have assumed is correct. So it's basically bootstrapping, creating a bootstrap world, assuming that the model you are assuming is the correct model. So just to give you an idea how you might go about using a parametric bootstrap, and again, this is programmed in various packages, but it's good to go through the steps in order to understand how parametric bootstrap works in this case. If I want to estimate the mean squared error of my theta hat I EBP, remember that this is an estimator of the mean, say, of income or a version of income, say, equivalized income in municipalities in Colombia. So what you do is you start with estimating the nested model, the working nested model. Say you have a preferred model that you have tested and you select it with your original data, with your ground truth data, the survey data, say the high access survey. So you estimate the model using the sample microdata, okay? And then by estimating that, you get estimates of the regression parameters and the two variance components. And what you do then is you're going to start generating data in a bootstrap world. So the second step effectively generates bootstrap area effects under the model, and under the model, we know that the UI, the random effect, is assumed to be normal with mean 0 and variance sigma squared u. And in order to generate bootstrap versions of the random effects, then what you do is you generate UI stars. Remember that stars represent quantities in the bootstrap world, and B represents an index for the bootstraps. Because we're going to repeat this bootstrap multiple times, we index the bootstrap by B. And the way you do that is under the model you assume normality, so you generate a realization of area effects under normal distribution with mean 0 and the sigma squared u. You have nothing else than the estimated sigma hat u that has been estimated with your original sample. So you save that, and then you go to step 3. Independently from the area effects, you generate a set of unit level errors, which we denote by epsilon ij. And again, these are bootstrap errors for bootstrap iteration B. Again, under the model, these are assumed to be normally distributed with mean 0 and variance sigma hat epsilon squares. Again, this is the estimated variance that you have estimated by using your original microdata, the survey microdata. So what we need now, we need two things. One thing is we need to calculate the true the true bootstrap means for each area. Okay, so you can do that by generating effectively the mean errors in area I, the mean epsilons in area I. So that, I describe them as epsilon I bar star B from this distribution here. So that will follow, because it's a mean, it will follow normal with mean 0 and variance sigma squared epsilon divided by ni. Okay, and then by using this, you can calculate the true bootstrap quantity of theta I in the population. That will be nothing more than x bar I. These are the true the values of the population mean, say, from the census or from some administrative data that you have available, times beta hat, that's the original regression parameters as estimated from the sample microdata, plus the realization, the corresponding value of the random effect that you generated in using step 2, plus the mean of the errors that you generated in step 4. Okay, and that will give you the true value, how the true value would have looked like, assuming that your model holds, right? So remember that with a model-based inference, assume that the y's are generated under a model, and as a result, it's like, as I said, you play goat here, right? Here, so I know how this data has been generated, and I can describe that by using a very simplified model. I know that device that I can use to play how the y's are generated. So basically, that's exactly what you're doing here. You say this is a likely set of theta I star in the bootstrap world, assuming that the model holds. Okay. Remember here that the computation of the true bootstrap means for each area does not require access to population microdata, right? You see, there is no population microdata. So for computing this, you don't need the population microdata from the census. You just need the aggregated axis, the population axis at the aggregate level. Okay, so what else?
Because I have a question.
Yeah, sure.
So in the previous slide, we saw that to estimate the Abp estimator, we use the sample, and also we use a synthetic covariators that we create, right? And we ponderate that with this gamma parameter. But now in the slide that we are seeing, we don't use a synthetic estimator, but we use this bootstrap with the information of the sample instead of the synthetic estimator. So we have the same effect or the same logic using extra data, but the difference is that the first one is a synthetic, and this second one part that are the bootstrap is with the bootstrap that is calculated with the sample data.
Sorry, hang on a minute. Let me start your question, Santiago. Stay on the microphone. It's fine, because we're going to have that an iterative discussion. So let me go first to the eBlap or to the blap or whatever. So this is the first part you're talking about. Is that correct?
Yeah,
so
yes, it is.
Okay, I'm not using anything synthetic here, right? What I'm saying. So basically, let me go through this. So gamma I depends on the two variance components. Y bar I is the sample mean in area I. X capital I is my population mean of the x's. That comes from the census or the admin data. The X small I is exactly the same, the means, but these are coming from the sample data, right, from your survey data. And the second part is 1 minus gamma I times HI transpose beta hat, okay? So when you say synthetic, what do you mean by synthetic here?
No, I think that you said that word synthetic, but also maybe I mean with synthetic because is this X capital is the census values or the administrative data values, so are the exactly population data.
Yes.
Okay, that's what I mean with synthetic, because we normally use the sample data, so the census data or administrative data is kind of auxiliary data or complementary data because we do not observe in all times.
Yes, yes. So the X's are population data. The X capitals are population values, right? Okay. And you assume that these are known, okay? Now, when I go to the Bootstrap, so in the Bootstrap, I'm using the same X's, right? I'm using the same X's, right? So whatever you use in your estimation with one sample, you still keep using the same X's also when you construct the Bootstrap, well, the Bootstrap values of the theta i's, basically. So this theta I star B is the true mean, right, that you would have observed, right? And how do you construct that? You construct that under the model, and this is the equal to the H bar. The H bar is coming from the census or the admin data, so nothing new here. The beta hat comes from the originally estimated parameters using your original data, right? The only thing that introduces here variability are these two components, basically. You have a new realization of random effects and a new realization of the unit level error terms, the average of this, under the model, and the model assumes that these two terms basically are normally distributed. That's it. That's the only variability that is introduced here, right? So you will repeat that many times, and each time you repeat, you will be able to construct a new set of true population parameters under the model, okay? What else you're going to do in step 6 is you're going to also generate a set of values of y as if effectively these values are your new sample values. Remember that under the model-based framework, the yi's are not assumed to come from this randomization distribution where the population is fixed and then you select repeated samples, but you assume that they are generated under a model. They are the outcome of a model, right? And that's what you're doing here. You say that my Bootstrap sample data, okay, will be Yij star B. They are basically the values that are calculated as Hij beta hat. Now, Hij here are equal to the values of your original sample, whatever you had in your sample data, the high X, times beta hat, the value of beta that you estimate from the original survey, plus then you add the realized Bootstrap UI, say in the first iteration of the Bootstrap, and then you add the realized EIJs also in the corresponding iteration of the Bootstrap. And using these values now, using the new Ys and the original X's, what do? You re-estimate the nested error model. Okay, so you re-estimate the nested error model, and with the newly estimated variance components and regression coefficients and so on, you get a new set of eBLAPs, okay, which I denote by theta hat I eBLAP. Now this set of new eBLAPs are denoted by star B because the new set of eBLAPs has been calculated by using the Bootstrap data, not the original data, but it has been calculated using the Bootstrap data. So in one iteration of the Bootstrap, you get two things. You get under step 5, you get theta I star B, and under step 6 and 7, you get theta E blap hat star B. Then what you do is you repeat that for a large number of times, say 500 times, 1,000 times, whatever. And at the end of this process, you can get an estimator of the mean squared error, which is going to be a bootstrap estimator, which is going to be, you're going to take the squared differences of the E-blaps that you have calculated in each iteration of the bootstrap, of the parametric bootstrap. Everything is parametric because you use the normality assumptions that we assumed. You are going to subtract the corresponding set of the true bootstrap population values, okay? You're going to square them, sum them, and then divide them by the number of iterations, bootstrap iterations that you run. And that will give you an idea about how uncertainty, how much uncertain, how much variable your estimated E-blaps are relative to the true values that you also generate in the bootstrap. Okay, so all of this hopefully will capture the uncertainty, because you see the theta hat E-blap star B is re-estimating the beta hats, but also re-estimating the sigma squared U and sigma squared epsilon. So the variance components will be re-estimated also again by using the bootstrap sample that you generate in step 6. Okay. Santiago, Reunión, Nels, is it clear, or is it are there still questions on this?
I have another small question, and it is in this first part of this slide. So in the last slide, we saw that we have those bootstraps, and the bootstraps were calculated with the census of administrative data. Mm-hmm. But these new bootstraps that we see in this equation, in the first equation, are calculated with the same census population data, or are calculated with the sample data?
No, here in this equation here that I highlight now, there is no census data, right?
Okay.
This is the X's from the original sample, okay, and the same UI stars and EIJ stars as the ones that you used before, okay?
Okay.
So once you start with iteration 1, you carry these UIs and epsilon i's throughout, okay? The only difference between step 5 and step 6 is here that you use the sample data, because here you're generating a realization of your sample, okay? And whereas in 5, you use the population data. But other than that, everything remains the same, right?
Okay, thank you.
Jose, you have a question.
Hello.
Hello.
But we use auxiliary variables, right? We don't usually, in this exercise, we don't usually only use the survey information, but we use as the we require more information in order to improve the estimates, right? It is true.
You require so if you can mute your, because I get the echo. Okay. Yes, if you are, so in order to fit the model, you use only the survey data. You don't need anything more. But if you want to predict the parameter of interest, which is like, let's say, the small area mean, then you need some additional information, and that is basically the population values or some population values of the X's. Okay. Is that clear, Jose?
Yes, in area level or unit level. When you say population values, I'm not sure.
So these are the X bar i's, the X bar capital I, right? So this is basically at the area level. For this exercise, we don't. For this particular exercise, we don't need population values for every unit in the population. We just need the aggregate at the area level. But this is only for this particular type of analysis, because we're estimating a mean. When we go to the poverty mapping methods, there you will require microdata. These X bar I's will not be sufficient. You will need to have the unit level microdata in order to do the prediction. Okay, but for now you just need the X bar I, nothing more.
Thank you.
Okay, Angela, do you want to come in?
Yeah, I just wanted to say it may be helpful to actually explain why that happens. I mean, the model is formulated at the unit level, but it's just that because it's linear, you could just add. And then because you can add, then you end up not actually needing the excess at the unit level, but just at the aggregate level. But the module was formulated originally at the unit level. Now, of course, as soon as you put anything like a transformation or a logit or any kind of things like that, then you cannot, the model is not linear anymore, and then you're not going to be able to just add. And that's where you have to actually require unit level data. But the model is formulated at the unit level, at the level of the units, rather than at the level of the areas. We're just using the trick that because it's linear, we can just collapse.
Exactly.
Is that helpful?
And this is, I think Angela, I think this is the equation here. So if you develop that equation here, you will see that because of the summation over the population units, at some point the X bar I, the population value, will come out. Okay, but this is, as Angela said, is because of the way of what we're estimating. Because remember that we're estimating a mean. Okay, so you take the sum of the X's. Okay, and that can be expressed as by just using the aggregates, right? That's okay, but it will not hold as long as you start introducing other things like transformations, as Angela said, or some other kind of function of interest. Okay, so but this is for small area means. Now, if in your case you were just interested in calculating averages of equivalized income in municipalities in Colombia, and that's it, okay, then you don't need to have access to census or administrative microdata. But if, as I believe is the case, you are interested in estimating other parameters of interest, then you will see that just having the aggregate population values will not be enough. Okay, you will need more. So just to summarize, for unit level models and for estimating small area averages, you need two things. You need one set of survey data that measures Y, the outcome, and X. And with this survey data, you estimate the model that you assume, and here we assume a two-level mixed model, okay? And the second thing that you need is for whatever variables are included, whatever explanatory variables are included in your model, you need also the corresponding aggregate population aggregate information at the level of the small area. That's it. You don't need anything else. And with these two pieces of information, you can construct your BLAP as described down here, or the eBLAP when you replace the variance components but the estimated values, and you can run your mean squared errors either using analytic estimation or using the Bootstrap. The Bootstrap completely doesn't assume anything more than the aggregate X's at the area level and the sample Y's and X's from the sample. That's it. Nothing more. Okay. So again, before I carry on, I look at Jose and Santiago, and if you have any, if it's still unclear, we can keep discussing it, or if you're happy, I will move on to the next slide. Shall I do that? Yeah.
Thank you, Nikos. Everything is clear.
Okay. Thanks, Jose. Although you have a nice background. Whereabouts are you? Good. Okay. Right. So what I'm going to do now is I'm going to give a summary of these unit level models. So up to this point, we have focused on estimating small area averages. Okay. Not currently for the type of applications that people want to do. This is not very exciting because remember that small area estimation developed many years ago, and people wanted to estimate averages, for example, right, or proportions and things like that, and they still want, actually. They're a big part of the application. But as these methods develop, people are coming up with all sorts more and more complex general parameters that they want to estimate. But here we have assumed that we're interested in small area averages. Let's see at the data requirements. That's exactly what we discussed now. So what do you need to do that? You need to survey microdata at unit level that include the target variable y and relevant auxiliary information variables x, hopefully that are predictive of y, otherwise it will not be very helpful. And you need also the area identifiers. You need the area identifiers because you need to know where to specify the random effect. Okay, sometimes you come across data providers that say, oh, we can give you survey data, but we cannot give you the area identifier. And that will not be very helpful. The second thing that you want is population means of which are denoted by X capital I for all the auxiliary variables. And because it's likely that the auxiliary variables, whether they come from population means or from census data or admin data, these X's are also assumed that are measuring the same variable, the same concept, okay, as the survey data. So that's something else you will have to be a bit careful about, because obviously what you are doing is you train a model using survey data. You take the parameters of the model and you apply the parameters of the model to these population values that are denoted by X capital. And obviously, if the X capital and the X are measuring completely different things, then that might be a problem. Okay, so obviously you need to be mindful of the definitions of the X's, both in the survey and in the census or in the administrative data. Okay, as we said, no unit level X's for the population is required at this point. Okay, so the only micro data for X's that you need are the ones that are coming from your survey. But for the out of sample data, for the out of sample units, you don't need to know the exact X's in the population. But that's purely because of what we are estimating here. As Angela said, these are linear statistics, and effectively you can replace the summation of the xij's by x bar. Santiago, you have your hand up again.
Yes, Nikos, I have a question. So you said that we have that we need the two data requirements, the survey and also the population means. But if I have I have the survey data at GRT, but my population's data is T-2. I don't know, is some years ago. Is this good, or this data can we use this data to replace the populations means in the GRT or not?
Okay, so that's a very good question. I don't know if it's good or bad. I'll tell you what I think it is, but the reality is that people do it. Okay, so if you see all the methods that have been applied, they're using census data, microdata, from 5-6 years ago, because the surveys are keep updating, but then because of what the people are trying to estimate, the census data are coming from a long time ago, right? I think this is problematic in some ways. I mean, I don't know how problematic it is. It depends really on what happens with what you're measuring and what happens with the X's. It will be application specific, it will be country specific, but it's something that you need to be mindful of. This is why I think that there are two things here. And Angela, please, switch on the camera and say your views if you have any other ideas. One thing is that I think we should be looking. There are methods now that are being developed to try and move away from assuming auxiliary information that is not time consistent with the survey, for example. Right? So you're trying to replace that. Of course, this comes at the cost of assumptions. Okay. The second thing you can do is effectively potentially to use area level models in this case, because the edges in area level models, you can have sources, auxiliary sources that are more frequently updated, okay, and more frequently updated together with the survey data. So that might be one way to try and benchmark or compare basically estimates and see perhaps if there are any issues with the auxiliary information that has been collected a long time ago. Okay, but I think this is something you have to be mindful of. And if you think, for example, that the distribution of the edges may look completely different for some reason because there is a structural break in the economy during that period and so on, or something has happened in areas that makes people, you know, being affected in different ways and compared to 10 years ago, I think these are things that basically might be quite problematic in terms of what you're trying to model. Okay, Angela, do you have any comments? No, she's quiet. Okay, so okay, so you know, I mean, but this is something, it's a very good question. I think you have to keep it in mind. Okay, I would say if you can move away from using old data in some ways, that's a good thing. That's why administrative data might be a good thing for you. The problem with administrative data is that sometimes they exclude key parts of the population. That's the other thing. You may not have a problem of timing, but you may have a problem of coverage with administrative data. This is something that you have to think. Okay, so what are the advantages? Obviously, compared to area level models, using unit level data allows for more efficient estimation of the model parameter. So it's effectively, when you aggregate the data and you use area level models, effectively like throwing information a bit away. So unit level models are using the entire data that you have available in your survey source. The EBP under the unit level model is a composite estimator that borrows strength over areas, as is the case with the area level model, the EBP under the area level model. It gives more weight to the regression estimator, to the survey regression estimator as the area size increases, and to the synthetic estimator as the area size goes to 0. So effectively, depending on how the sample size operates, depending on what happens with how good your model covariate, the covariates that you include in your model are, that will determine the sizes of sigma u and sigma epsilon, and that will determine the sizes of the shrinkage factor, the gamma i's, and as a result, it will determine how much weight you give to one part and how much weight you give to the other part. Okay. In contrast to the Fay-Herrott model, you don't need to know about the sampling variances. Okay, so remember that with area level models, you had to estimate the sampling variances and of the direct and assume them fixed. Whereas here you don't have to do that because you use unit level data. You can estimate both variance components, both the sigma u and sigma epsilon. Okay, and estimation of out of sample areas. Those municipalities in Colombia that have 0 sample sizes is also possible, as is the case with a unit level model, with area level model. So remember, you use a synthetic estimator for those areas. Let me just go back to remind you, it's this estimator here, right? Theta hat I is nothing more than x bar I beta hat. You don't have a UI, because the UI, the area effect is area specific, and you cannot estimate it for areas where you have 0 sample sizes. Okay. So things to consider with a unit level model. So obviously, the estimates are based on a model, and being happy with your model, do the model checking, the model assumptions, the model selection, and so on is crucial. As you saw, it's not only the point estimates, but it's also the mean squared error estimates. If you use Bootstrap and if you use the Prasad-Rao analytical estimator assuming normality, then this is going to depend on assumptions. the sampling design is not accounted for in the model that we presented here, right? So if you wanted to do that, there is literature which allows you to account for the survey weights in the EBP, and one of the papers that has been used quite extensively in the past is a paper by Wu and Rao, which proposes a pseudo EBP. Okay. Estimates can be affected by outliers, right? I mean, especially when you model income data. Obviously, just modeling the income is not going probably the model assumptions and the normality assumptions under the basic model probably are not going to hold. The most typical way of solving that problem is described in the last bullet point in this slide, is effectively to use transformations, right? And as we will see later on with the poverty mapping methods, the method that has been the preferred method by the World Bank is also assuming a logarithmic transformation. And recently there have been papers where papers that have been proposed the use of other types of transformation as opposed to just straight logarithmic transformations. And that can make a difference. There is literature about outlier robustness, small area methods, but for the purpose of what you're trying to do at the moment, I think that the use of transformations, as we will see later in the next, later on in the poverty mapping methods, will be a good way of doing things, I think, and at least testing the methods with transformations and seeing what difference they make. Okay, so other things to consider. As I said, the requirement for microdata may cause issues with accessing the data. Obviously, you guys may not have a problem because you are already within the organization, but generally speaking, it's something to consider. If you don't have unit level data, then area level models are the alternative model-based method. The most widely used analytic mean squared error estimator by Prasad and Rao is second order unbiased under the model that assumes normality, so that's a good property. For more complex target parameters and models, the standard way of estimating the mean squared error will be parametric bootstrap, as we will see. And what we're going to do now is we're going to start describing methods for estimating general parameters, and the emphasis will be on poverty mapping. Okay, so we're no longer going to estimate small area means. Small area means will be a byproduct of the poverty mapping methods because there will be a standard output, but on top of that, you will be able to estimate other more general parameters. Okay, so what I'm going to do now is I'm going to let me see how we go in terms of people. Okay, Santiago, I'm going to admit him. Okay, so what I'm going to do now is I'm going to just give you an illustration of what we'll try to do for the last hour of this session. So these are some typical results of poverty mapping. On the left-hand side, you have a map. By the way, does anyone recognize what area is that? Any ideas? Nah.
Is it Colombia?
No, it's not. It's a difficult one because it's not an entire country. It's a zoom within a country. Is the area around Mexico City. Okay, so it's the state of Mexico. Okay, so the left-hand side is the headcount ratio. These are estimates of the headcount ratio. By the way, these are municipalities. So the reason that we selected it's interesting because also in Mexico they have an interest, I think, in municipalities as an administrative level, and these are basically the geographical boundaries there present boundaries of municipalities. So the left-hand side is giving you headcount ratios, estimated headcount ratios for municipalities in that state. The middle one is poverty gap, and the last one is Gini coefficient. Okay, so that's what you are typically interested in estimating. You may be interested in estimating a median equivalized income, right? So that's another parameter that you might be interested in finding out about. Okay, and so what we're going to do now is we're going to see methods that will allow you to estimate those types of parameters for small areas. So as I said, typically methods focus on estimating means. Newer developments in small area methodology allows for the estimation of more complex parameters. And the methodology is general and can be used to estimate a wide range of parameters, okay, as we will see. So once you assume that the model is correct and you believe in your model, then you can construct estimators for different types of parameters. So poverty mapping methods, I'm going to focus on the first two in this training. That's what we're focusing on, is the method by Elbers et al., the ELL method, as is going to be abbreviated, and that method is described in a paper in Econometrica in 2003, and it has been a very popular method, especially in applications around the world. And the second method I'm going to describe is what is called the empirical best predictor, or EBP method, that was proposed by Molina and Rao in 2010. Okay, and these methods are operating with the same model, the same model in terms of both using a unit level random effects model with some differences, depending on the configuration of your data in the areas, they may be very similar or they may be different. And that's what we're going to try and describe. I'm going to try and describe what are the differences between the two methods. And I'm giving you some references down there. Area level models for general parameters have been proposed. And I know that, Jose, you asked me in one of the previous sessions about area level models and more general parameters. So it has been proposed in the literature, but just in a moment I'm going to say what is the difficulty with that. But it is possible. I mean, there is literature out there that can help you to use area level models to estimate general parameters. Okay. In this training, we're going to focus on methods based on unit level models. So the ELL and the EBP method, so these two methods are using unit level models, okay, not area level models. We're going to focus on unit level models, so basically what we described just before. So what data do we need to have in order to implement the methods? We need the estimation requires access to unit level population auxiliary information. In other words, census type microdata, okay, or administrative type microdata that cover the entire population. So unlike the basic model that I described before, which is the Batiste, Harter, and Fuller model, in this case, we need to have access to population level microdata. As Angela said, this is because the target parameters are no longer linear functions of the data, as in the case of averages. In the case of averages, the parameters are linear functions of the data. However, with more general parameters, such as the poverty gap or the Gini coefficient and so on, this is not the case. Okay, so in this case, data access can be difficult. Okay. Even if you have access to the data, the point that Santiago raised earlier, it may be that the microdata that you have are coming from a long time ago, and that can raise an issue. So you need to be very mindful of that and be aware of that. Of course, use of area level models is possible, but the use of area level models for general parameters presents other challenges. And the problem is, one of the problems is that direct estimation with small samples for general parameters is not generally designed unbiased. Remember that the Fay-Heriot model assumes that you have a design unbiased direct estimator of what you're trying to estimate, such as a mean or a proportion. However, if you had a Gini coefficient, for example, or a tail index, this might not be, for small samples, will not be designed unbiased. And some of the methods that use area level models propose bias correction methods before going into estimate the Fay-Harris model, to fit the Fay-Harris model. But it is possible. The literature is out there, and it is possible, but you have to be careful with what you're modeling. Okay. Okay, let's look at the first method, which is what we have abbreviated as ELL method. So Elbers-Lanzhou and Lanzhou method. Can I ask you, have you done any applications with these methods? Because I'm aware that you're doing something with poverty mapping at the moment. So have you applied any of these methods at all? Jose, do you know, or Santiago, or someone else?
In our testing, at least we haven't.
You haven't.
Maybe,
okay.
Maybe in Colombia, in Colombia we have another state agencies that may be interested in poverty mapping. So it could be possible that they have used it.
Okay.
Like Departamento Nacional de Planeación, DNP y Departamento de Prosperidad Social. One agency is about political, only economy policy, and the other one is the one that is in charge of cash transfer programs.
Okay. Okay. Well, I mean, I'm going to describe the methods, and then, you know, but I wanted to know whether you had any past experiences with those methods.
Just to complement something that Jose said, is that the models that we used are mainly machine learning models like logistic regression and some decision trees and random forests, maybe. But
okay.
That's the models that we are using in this exercise.
Okay, but that's relevant, Santiago, because you will see, I will give you some references to, for example, poverty mapping with random forests as well. So it is relevant, and it will be interesting to see if you can use the data that you say in your random forests or whatever other methods to try and replicate the exercise with one of these methods to see what happens. I'm involved in some work at the moment with random forests for poverty mapping, and it's interesting that it can give some advantages, but it's interesting to see what your results are and how you think that they're working. So let's go through the ELL method. Okay. It has been used, as I said, quite considerably to estimate indicators of monetary poverty for small areas. So how the method is working, and that's generic. Before I go into the nuts and bolts of the method, the method works effectively by simulating an entire population. So basically, you assume a model. And by assuming the model and by having access to the census microdata, what you do is you use the model to simulate an entire synthetic population of households, and effectively that simulated data set, that simulated synthetic census is the one that you use in order to estimate what you want to estimate. Because if you have the entire census data and you have an income values for the entire population, then you can compute whatever you want to compute from that. It can be a headcount ratio, it can be a poverty gap, it can be any general parameter that you might be interested in. So effectively, you predict the entire distribution, right? Obviously, you can also estimate simpler statistics like means, but also more complex statistics. So let's look at how the method works. Okay, so the ELL uses, as I said, a nested error model, so a random effects model. The left-hand side is the logarithmic transformation of the income or an expenditure variable or a consumption variable, depending on what you're modeling. And instead of updating the EBLAP, the predictor effectively uses a marginal expectation, and the whole thing is approximated via Bootstrap. Okay, so one comment about the specification of the random effects in the original paper that Elbers, Lanzhao, and Lanyao wrote. They specified the random effects at the level of what they call the first stage things, like the clusters, not at the level of the area of interest, not at the level of municipality, but at the level of the clusters. This is in contrast to what small area methods are doing, where effectively the random effect is specified at the level of the target area. So if you look into the traditional small area literature, the random effect is specified at the level of the municipality in the case of Colombia. For now, we're going to assume that the first stage things are the same as the areas of interest. Okay, that's what we're assuming. However, there are methods that allow both for cluster and area effects. For example, there are methods that have been proposed that instead of having a two-level hierarchical structure, they have a three-level hierarchical structure. So you have clusters, households within clusters, and then within areas. Okay, so that's possible. But we don't need to occupy ourselves with these models. At the moment, we're going to assume that clusters and areas coincide. Okay, so that's what I'm going to use in order to describe the method. So let's look how the ELL method is working. The ELL method says that my Yij is equal to the logarithm of the expenditure or the monetary measure, whatever that is, plus a shift parameter C greater than 0, so that we can make this quantity within the brackets to be positive. Okay. And then what it is assumed is that you use the Yij's to specify a model that is basically the same model as the one that we described before. Yeah, it's a two-level random effects model. So you say that Yij, which is logarithm of Eij plus C, is equal to Xij beta plus Ui plus epsilon ij. Okay. Now, and the model that we're using here basically assumes, basically the model that we're assuming here basically assumes that the between variance component, the variance components are constant, but you could extend the model effectively in order to make that to be more, to account for heteroscedasticity, non-constant variance, and so on. Okay. So the ELL method works as follows. What you do is you take your survey microdata, okay? So think of the survey microdata as your the Hayatsu survey, and you use some kind of least squares method to estimate the model parameters beta. Okay? So you get beta hats. And then what you do is you compute unit level errors, which we denote here by Vij, to be the difference between Yij minus Xij beta hat, so that these are basically residuals. And then you split the unit level errors into an area specific error, which is nothing more than the average of the unit level errors in each area, and is denoted by Ui, and another part which is denoted by Eij, which is basically Vij minus Ui. So you take the unit level errors and you subtract the area level errors, and that will give you the Eij. Then what you do is you create versions of Ui and Eij by sampling from the empirical distribution of the residuals, not by some normal distribution, but you say, I have a set of UIs, I have a set of epsilon ij's, and I'm going to sample one UI and I'm going to sample one Eij. And once these have been sampled, then you say that my the value of my income, okay, or expenditure, the value of Yij star in the population is equal to Xij beta hat okay, plus UI star plus the epsilon ij star. Okay, now here this xi is the population microdata. Okay, these are the population microdata. So basically what you say is that I'm going to assume a model and I'm going to use the model and the population microdata in order to simulate a synthetic version of the population of income values. Okay. And you use these Yij stars to compute any area-specific target parameter. So from this, once you have done that for every unit in the population, so think about that, it can be millions of records, right? Because you have millions of people in Colombia. Then you have a complete set of income values, and then what you use, you can use this complete set of income values to compute a mean, a median, a headcount ratio after you define a poverty threshold, a poverty gap, an inequality index, and everything else you want. Okay, so the method is fairly simple, right? You just fit your model, you calculate residuals, you split the residuals into unit level and area level, and then you simulate realizations of these error terms, the area level error term and the unit level error term from the empirical distribution of the error terms. Okay, so what you do then is you repeat that process many times. So instead of selecting generating only one possible set of income census values, population values, you generate a series of censuses, okay, maybe 1,000 censuses, as many as you wish, and each time you generate a new census, you calculate a new value of the parameter of interest, which is denoted by theta I star h. Okay, and the ELL estimator of the parameter of interest is nothing more than the average of the expectation, the summation of theta I star h over the number of times that you have, the total number of times that you have used in order to replicate the entire process. Okay, and the way that the paper proposed to estimate the mean squared error is by taking the square differences of the theta I star h minus theta hat I ELL, square it, and then divide it by the number of iterations that you're using. Okay, so basically it will tell you how variable your estimates of the ELL estimates will be, and that is relative to the theta I star h that you are generating in each iteration of the ELL process. Okay, that will give you an estimate of the mean squared error. Okay, so it's purely numerical. Of course, it relies on fitting what is a two-level nested error model, but the process is purely numerical and gives you, and it assumes the use of census microdata and the replication, the creation of a number of population data sets that you use then to calculate whatever parameter of interest you are interested in. So the trick is you need census microdata, right? If I don't have census microdata, I cannot really generate my populations, right? Is that clear? Everyone is very quiet. So have I lost you, or is that clear?
No, everything's clear.
Yeah, that's clear. Angela, do you want to add anything, or I don't want to be picking on you all the time? But,
no, it's fine, Nikos. I'm fine.
Okay, good. Okay, let's look. So this is the Ell method in relation to poverty mapping. I mean, this doesn't quite add anything to what I have already said. It's just because I suspect that you might be interested in some poverty measure. I mean, the typical papers that you will read around the Ell method, they will define some poverty measure out of this FGT measures, okay, that are defined by this formula. The key thing here is that the Z here is a Z. The Z is a fixed threshold, poverty threshold. So it will depend really what kind of poverty thresholds you use in Colombia, and alpha here, depending on whether you set, say, alpha 0, 1, or 2, will give you different values, okay? So if you set different parameters, it will define different parameters. So if you put alpha equal to 0, this thing will disappear, and what you will be summing over is basically an indicator function that indicates whether the corresponding monetary monetary measure is less than the poverty threshold or not. If it's less, then that's a 1. If it's greater, then it's 0, and that gives you a way of calculating the headcount ratio. And the same thing for poverty gaps and poverty severities, depending on what you might be interested in. So the other thing that you have to be careful, remember that the model uses a logarithmic transformation, okay? And obviously, in order to go back to the original scale, you have to take the exponential back transformation. You should apply that. And then once you apply the exponential back transformation, then you will have a set of incomes or consumptions or expenditures in the population, and you can use this in order to construct the estimator under the Ell method, depending on what measure you want to define out of these FGT measures of poverty. Okay, so really there is nothing. There is no information here other to say that this is how you apply the method if you were interested in estimating the headcount ratio, the poverty gap, and so on. But what is important here is that you need to apply a back transformation in order to go, because remember that the model is defined on the logarithmic scale, and when you do all the estimations here, all the estimations are on the logarithmic scale. At some point, when you arrive at this point here, you want to back transform to the original scale in order to have the incomes back on the correct scale. And because you use a logarithmic transformation, the simplest, the back transformation is the exponential function. Now, I'm not going to say a lot about this here, but normally, if you back transform, you will introduce bias, especially with the logarithmic transformation. But here you don't introduce bias because you are using the census microdata. Okay, so there is no reason to add any kind of bias correction here. Okay, if you didn't have census microdata, that will be a different story. So if you were applying a logarithmic transformation, say on the model that I presented before, where you had only the H bars, the population totals, the population aggregates available as part of your dataset, then there will be some need to add the bias correction. But I'm not going to confuse you with that because that topic can get technical, and also it can take a bit of time to explain. So, but here we have census microdata. So using transformations and using back transformations is not going to cause you any trouble, assuming that you have the population data available at the unit level. Okay, so let's look at the Ell method. So with the Ell method, as it was proposed in 2003, we don't assume normality. Okay. Later in this section, we will see that under normality, we can define what is called an empirical best predictor, and that can give you some advantages, as we will see. The Ell method does not condition on the sample data. Okay, so you don't really get a correct area-specific prediction, and because you average over all these bootstrap samples, remember that effectively you do a bootstrap here. You select repeatedly from the set of empirical residuals, and you construct a hypothetical population. Right? If you average all of this, if you take the expectation here of Yij, okay, that will be equal effectively to Xij beta hat, which is a synthetic estimator. okay? Because the expected value of UI is 0 and the expected value of EIJ is also 0. So that leads to a synthetic estimator, okay? So if you have an application where you have many out-of-sample areas, then the ELL method will give you estimates that will be identical to methods that condition on sample data. So the ABP, you will see that the ABP method conditions on the sample data, okay? And the ABP method and the ELL method can be different for areas where you have sample data. However, if you have areas where you have out of sample data, then the ELL method and the ABP method will not give radically different results. They will be almost identical, the results. Okay, there may be differences because of the way the model is fitted slightly, but the results will be identical. Okay, so this is something that is important to consider, especially when you look into the application in DANE, because if you have many municipalities that are out of sample, then that may make you think that you may go one way or the other way. It's something that it has to be discussed. As I say in the last bullet point, if you have many areas that are present in the sample data, then the methods that condition the sample data will produce more efficient estimates. Okay? Question?
Sorry, Nikos, one question. I think that I don't get completely the expression that condition on the sample data. I don't completely get it. Could you please elaborate?
I'm
condition the sample data.
Yes, that probably will become clearer. Okay, when I will present the next method, Jose. So if you bear with me, right? I have included things here that assume that you have to see the next method, and then we can go back to this and you can see the difference, okay? So let me give you the summary of the ELL method. The data requirements, you survey microdata at individual level. So as before, like in the hierarchy, you need the target variable, relevant auxiliary information, area identifiers. The second thing that you need is census, register, admin data, microdata for the same auxiliary variables, measuring the same concept for the areas of interest. Okay. The unit level auxiliary information is required for all units in the population. And ideally, you may have additional information like contextual variables for all areas of interest that might help you to reduce the unexplained between area heterogeneity, like the sigma squared U. If you have contextual variables, you may want to include them in the model because they can help you reduce the unexplained heterogeneity. What are the advantages? Based on unit level data, it's based on unit level data, so you have more detailed information than in area level data. The entire distribution is predicted, is generated, so any parameter can be defined as a function of the data, can be estimated without refitting the model. And you don't make normality assumptions here, at least in this version of the ELL method. The disadvantages, the ELL estimators may have a high mean squared error estimator under the model, okay, and possibly a worse performance than direct estimators if there is high between area variability. So if your sigma U is very high, then the ELL estimates may not be that good. Obviously, the estimates are based on a model, and model selection in residual diagnostics is needed. The estimates are not designed unbiased and can have considerable bias under informative sampling design. So there is no accounting for sampling design in this version of the method, and the estimates can be affected also by outliers. Okay, let's contrast that against a different method. So, and that's the empirical best prediction method. So this is the method that was proposed by Molina and Rao, specifically for estimating also poverty measures. So effectively, the 2010 paper was an attempt to bring the poverty mapping exercise into a more traditional small area estimation framework, and contrast that against the ELL method that had been proposed about 7 years before in this Econometrica paper. So under this approach, as we will see, the estimates of the unobserved data are obtained as the conditional expectation of the unobserved data given the sample data. So basically, you say I want to calculate the expected value of what I don't observe given what I observe. That's what I mean by conditional expectation. Okay? And assuming normality for the model error terms, you can define a best predictor that can be approximated via Monte Carlo simulation and using univariate normal distributions. Okay? So under normality, you can define this empirical best predictor, and the empirical best predictor is the expected value given the sample data that you have in your sample. Okay, so the best predictor depends on the unknown parameters, and by replacing the unknown parameters with estimates will lead to an empirical best predictor. So basically, it's exactly the same discussion that we had before. Basically, you have a form of a best predictor, you have unknown parameters, you plug in estimates of these unknown parameters using some statistical method, estimation method like maximum likelihood, and then that will define you the empirical best predictor. The EBP method works very similarly to the ELL method. So what we're going to do also with the EBP method is we're going to simulate a synthetic census, multiple synthetic censuses of the variable of interest. And then for each of these synthetic censuses, we're going to calculate the value of the parameter of interest. Okay, so the method is very similar. The difference between the two methods is technical differences that I'm going to hopefully describe in this slide. Okay, so the EBP method uses exactly the same model. Okay, look at this model here. Is exactly the same model as before. So my Yij, think of that as logarithm of income plus a shift parameter, is equal to Xij beta plus Ui plus Eij. Okay. What you do with this is to use the sample data to estimate the parameters of the model. So beta hat, sigma hat u, sigma hat t, and the predicted random effect, ui. And when you have all of these parameters, you can get an estimate of the shrinkage factor gamma I, which is equal to this expression here. So what we need to do now is we need to calculate the expected value of yr. Remember, r is the portion of the data that I don't observe, right? Because I have not sampled the entire population. So I want to calculate the expected value of what I don't observe given what I observe, ys, under the assumption of normal errors. Okay? And because I'm assuming normality, okay, I know the form of this conditional expectation. This conditional expectation will not always be, it will not be possible to calculate it analytically if for any distribution, but under normality, you know what is the expected value of yr given ys. Okay, and in order to do that, you can use a Monte Carlo approach to computing this. How do you do that? You say that I'm going to generate error terms, unit level error terms, Eij star, from a normal distribution with mean 0 and variance sigma hat E squared. And I'm going to generate random effects ui from a normal distribution with mean 0 and variance sigma hat squared u times 1 minus gamma I hat. That comes directly from multivariate normal theory that tells you how this distribution will look like. Okay. So if I know what is epsilon ij star and I know what is ui star, okay, what I can do is I can simulate a synthetic value of income, okay, yij star heights, right, as hi beta hat plus u hat I. Now the u hat I is the random effect that I predicted with my original sample, with my Hayachi survey, right, plus uij star plus epsilon ij star, okay? So basically you see that that is my conditional expectation, okay? So my YIR given YIS follows a normal distribution with mean this and variance that basically is calculated by generating error terms according to these expressions up here. Now, let's stop here for a moment and see what is the difference, what are the similarities and what are the differences with the ELL method. First of all, both methods are computer intensive, so both methods are basically simulating an entire population. And both methods require the use of census microdata. So your HIJs here are data that are available for every unit in the population. Okay, so these are the similarities. What are the differences? You see that under the EBP method, we are assuming normality for the error terms. But precisely because we are assuming normality, we're able to calculate this expected value of YR given YS. Okay? And the second thing is because we condition on the sample data, you see that here you get the predicted random effect from the original sample data that has been estimated with the original sample data added to the predictions under the model. So basically you take Xij beta hat plus Ui hat. With the ELL method, you didn't have this Ui hat. That was not there. Okay, so if I go back to the ELL method, you will see that the ELL method, you see, these are the values of yi star. This is how I'm generating synthetic population values as Hij beta hat plus a realization of ui star plus a realization of Eij star, but I don't have a ui hat here. Whereas under the EBP method, because I condition on the sample data, you have an additional term in this prediction. Now, if many areas are out of sample, so if for many areas you don't have any observations, then you cannot calculate this ui hat. So that looks, if I cannot calculate this ui hat, then these values here will look similar to what the ELL is doing. Basically, you take the Xij beta hat, you add a ui star plus an epsilon Hij star. But if you have areas with sample data, and if you can predict the random effect, then this method will be different and will be more efficient. Okay. So effectively, you what you do is you generate multiple censuses under this model, under this expression here. Okay. And for the multiple censuses you are generating, you are calculating for each of these censuses the set of parameters that you are interested in, and then the empirical best predictor of the parameter of interest, which I denote by theta hat I EBP, is nothing more than just taking the expectation over the Monte Carlo iterations that you have done. Okay, so this is a Monte Carlo based method that assumes a unit level model, assumes normality for the error terms, and then it says, well, under normality, what I want to predict is what I don't know. So YR. So what are the incomes of those households that are out of sample? Sorry, that I don't observe in my sample, but they are in my population, given what I have observed in my sample. And because you assume normality, you can calculate the form of this expectation, right? And that leads you to this expression here. Okay. So you see that this expression here will give you a way of simulating the entire distribution of income in Colombia, and you know how this income will look like in each one of the municipalities in Colombia. It's a totally purely model-based method of simulating population values. And you can use in terms of mean square error estimation. So if you want to calculate now the uncertainty that is associated with these empirical best predictors, whether that is a headcount ratio, a poverty gap, a poverty severity, an inequality index, or whatever it is, the method that has been proposed for mean square error estimation is parametric bootstrap. What you do is you feed the model to the original data, you generate bootstrap versions of the area effects and the level 1 error terms, okay? And then you construct a bootstrap populations using the model. So this is your model here. You say that my Yij star is xi beta hat plus ui star plus epsilon I star. Okay, so you have bootstrap populations, you compute the population value in each bootstrap population, you have a bootstrap sample, and then you implement the EBP method. So for each bootstrap sample that you are selecting, you are implementing the EBP methodology, and then at the end, the mean square error estimator is they are the square differences between the EBP estimates and the true values in the bootstrap population. Okay, so it's a purely parametric bootstrap. Okay, so Jose, yes.
Sorry, I don't know. Maybe I've been with connection problems, but I don't get the part of U hat. Where do you estimate the U hat in this framework?
The U hat, Jose. The U hat, Jose. You mean this U hat here, right?
Yes.
This U hat is basically the U hat that you estimate by fitting the model to your high-access data. So you have data, the survey data, okay? You fit your model to the survey data, and you get your U hat. That's the U hat from the original data, using the original data. That's where you get it from.
Okay, and the other terms of the model comes from the sampling. When
beta
you
hat
say sampling, yes, no. The other U comes from the sampling. Yes.
This U star
and we in the sampling we get these other terms, but how do you assign? How is the relation? How do you get the relation between the individual I and connect that individual I to their value U, to their value U in epsilon?
The I is not an individual, right? The I is the area. Okay, so you have a set of x's in the population, right? For each you apply the beta hat. Each x will be in one area. Okay, so depending on what area you are, you add a UI star, and then you also add you generate a vector of EIJs that are equal to the population size. So if you have 150 million, you generate that as well, and then you add it to the to your vector. Okay, that's it. It's purely synthetic.
Can I say something?
Yes.
So individuals are J.
Sorry, the U.
The individuals are represented by J. Sorry, by J.
Yeah. So you have
J.
You have individual.
Not by
J
I, but
living in area I.
You have individual J and area I.
So how do you assign the epsilon to individual J? How do you know when you sample or
let me try to jump
over
in
the
that.
over your
Let
normal
me try to jump in
distribution?
there a little bit to see if it helps.
Okay.
So basically, with the case of the ELL, did you understand how that worked in the ELL? If you go back to the slide of the ELL, you said you had random errors, EIJ, and you had terms UI as well, and you were resampling from that fixed set in the ELL. Here, those EIJs and the EIJs, the epsilon IJs and the UIs were results from the model. Those were residuals, level 1 and level 2 residuals from the model, and you would just select a random sample from those and add them to your observations. So there is no specific IJ that is going to match to that IJ. You're selecting, you have 100. Okay, in Colombia, you have 45 million people and you have 1,000 areas. Okay, so you fitted your model over the areas that you have in the sample, and you don't have 1,000 areas. You have only, I don't know, 300 areas in the sample. So that means you only have 300 UI stars. Okay, and now you're going to resample from those 300, 1,000 with replacement, and those are the UA stars that you're going to allocate randomly to the 1,000 areas when you go back in the census. And you don't have 45 million of people in the survey, you just have 280,000 people. So you have 280,000 residual terms in the survey, and you're going to resample among those 280,000, but now you're going to resample 45 million, and those you're going to add to the predictions in one census. And then you repeat the process, so you resample again, and there may be others that are allocated to a given area and to a given individual, and then you resample again and so on. Is that bit okay?
Yes, I have connection problems, but I think I get it. So in this resampling, we don't have any role with the auxiliary variables. Auxiliary variables in my values that doesn't play a role in my epsilon value.
No, you're just resampling residuals. Okay, now if you go to the EBP makes a distributional assumption. The EBP assumes that the U's are normal and the E's are normal. So actually you have a better way of sampling than just resampling residuals. So because in that model, you assume that the UIs and the epsilon IJs were coming from a normal distribution with a given mean and a zero mean and a given variance. And you already have gotten estimates for those variance components because you took the sample, you fitted the regression model. That means you got beta hat, but you also got the variance of the error terms at the level 2, the U's. You have an estimate for that variance, and you have an estimate for the variance of the epsilons. Then you can sample from a normal distribution. So instead of resampling residuals, you're going to have 1,000 areas. So I'm going to generate 1,000 observations from a normal distribution with mean 0 and variance, the term that you have there, sigma U square hat times 1 minus the shrinkage factor of that particular area. You generate a sample from the one observation from that distribution, and that is going to be the residual, the UIs that you're allocating to that particular area. And then you have also an estimate of the variance of the errors at the level 1, sigma epsilon squared. So now you're going to generate 45 million observations from a normal distribution with mean 0 and that variance. And those are the EIJ star terms that you're going to add to your prediction. And that is in one census. Then you need another census. So you do the whole process again and you get another set of residuals. And you do the whole process again and you get another set of residuals. Now the UI hat term here, that is fixed. because that is true. That is a real one that you estimated from the survey. So in every census that you're calculating, the UI stars are changing. The E epsilon ij stars are changing. The UI hats, those remain the same because those were those that you estimated from the survey data.
Yeah. So I think the confusion, you don't, in some ways, you don't, how can I put it? You can simulate the entire population, Jose, because you're generating from a normal distribution. You can generate 50 million replicates from a normal distribution. It's not a problem. Okay. Whereas in the other case, you have a finite set of residuals, and basically you are selecting them with replacement. Okay. And then you add them basically to the HI betas, right? Is that clear?
Thank you.
Yeah, good.
Thank you. In either case, it doesn't matter what are my values in the explanatory variables. It doesn't matter who I am for my residuals, for this kind of residuals.
No, what matters, not for the EIJs, not for the EIJs, because the EIJs have controlled for the X's, right? So basically you're sampling something that doesn't really, yeah. But for the UIs, it matters in what area you, well, I mean, it matters, you only sample as many random effects as the number of areas. So if you have 100 areas, you will have a replicate, you will sample 100 values from a normal distribution. What matters is that the households that belong to the same area are getting the same UI. Okay? Are you with me?
Yes. And expansion, when in some cases when we sample, when we are bootstrapping or resampling, we might use factor expansion. We don't use factor expansions to sampling in any steps. We don't like in the step where we construct the census data. In the first step, when we simulate the census data, we don't use expansion factors.
No. Okay. You mean expansion factors as in kind of the design weights or stuff like that? Yeah? No.
Yes.
Okay.
Okay. Thank you. And also, I want to share with you some of our numbers. We have 53% municipalities in the normal house in our household survey of the total municipalities in Colombia, and for 2021 we have a parallel household survey because we changed the census, the framework for sampling, the framework for the sampling, because the one with 50% is from 2005, and the new one that began in the last year is from 2018 census. In this new household survey, that also is going to be the survey for poverty estimates. In the future, we have we have 53%, and we have the complete departments, the complete country, and in the old one we have only 30.
Of the probably dropped.
In the past one, and now we have 53%. So I think that my connection got lost, but in summary, we have 39% municipalities in our sample in the household survey, which is based in the 2005 census. Now, in the new household survey, we have 53% municipalities in our sample, and also we have the complete set of departments, not only the 24, but the 33 ones.
Okay. Okay, so it sounds like there are many municipalities that are out of sample. But that's okay. I mean,
but you have half of them.
You have half of them,
It's
yeah.
much less than before, but it's still, you have half of them.
Yeah, I mean,
yeah.
the other question that is relevant there, Jose, is okay, if out of these half municipalities, 50% of municipalities, there are some that were not selected, but they had the chance to be selected. Okay, we can make some assumptions, but if they are not selected because they were not included in the frame or whatever, then that brings us to the discussion you had with Angela last week, I believe, isn't it?
Yeah, but I suppose that if all departments are covered now, then now we're going to territorios nacionales, so everybody should have a positive probability to being selected.
Okay, so all compartments means that also these the national territories are also potentially covered, okay?
Imagine, yeah, which were the only ones that didn't have a positive inclusion probability before, so I guess now we're going there. Good.
Okay, good. Okay, so in that case, okay, so what you describe, okay, is because 50% of your sample, 50% of the municipalities are in the sample. For this 50% of municipalities, you can apply the EBP, right? Because
there is something that I wanted to ask you about that.
Yeah.
Because there is conditioning on the sample and there is conditioning on the sample.
Okay.
I wanted to gather your thought on that, because when the EBP conditions in the sample, you have two things. One thing is that now you're able to get that UI hat estimate, that predicted random effect, which is going to help you in theory improve, going to get you a better predictor for the out of sample areas, for all the out of sample units. But also, that also means in your first item there, when you say compute expected value of YR given YS, what happens with YS? So that means that you have somehow matched also the survey and the census, and you're using the true income for everybody that was in the survey, or are you predicting everybody?
Okay, very good point. Very good point. Let me see where I have that. Here. So Angela is right. Because the condition on YS, you assume that you can link the census to the survey. Okay. However, in reality, such a link will not be easy. Okay. So, and if you have absence of linkage between the survey and the sample, what you do is you ignore the sample observations that are coming in the sample. So you ignore the Ys that are coming in the sample, and you predict for the entire population. And that assumes that the ratio between the sample size in the area over the population size in the area is small. Okay, so basically you say that the direct part doesn't matter. And because the direct part doesn't matter, I don't need to link. I'm going just to simulate the entire population of Ys under the model. Okay. Does this answer the question, Angela? Yeah. Okay. So going back to the discussion we had, just now, Jose and others, for 50% of your municipalities, you are able, hopefully, to get a UI hat, and because you will get a UI hat, you are able to predict you are able to predict to add this to the predictions, right? For the other 50% of the municipalities, the Y hats will be missing. Okay, so for 50% of the municipalities, your estimates will look a bit like the ELL estimates, and for 50% of the municipalities, you will have another part that is added to the model. Obviously, if your model is very good and you reduce your sigma squared U a lot, right? The between area variability, then maybe the UI hat may not play such a big role. Okay, that's also a possibility. So that depends really on how you build your model, what covariates you have in, and so on, and how your model predicts. Okay. So I'm going to finish here. I just had some very quick comments on the methods, and I would say that, as I said, the EBP method conditions on the sample data, and the area effects are predicted correctly. Okay. Notice that in contrast to the ELL, the predicted or the simulated population values under the EBP include that additional random effect, the UI hat, that is estimated with the original data. Okay, so that's a difference between the two. The EBP method performs better than the ELL in the presence of significant unexplained between area variability. But if you don't have a lot of between area variability because your covariates explain a big part of that, then the two methods may not be very different. For sample area, for in sample areas, so for 50% of the data, the cases in Colombia, the EBP method potentially offers more efficient estimates than the ELL, but for the out of sample areas, the performance of the two methods is almost the same. And the two methods also perform similarly when the between area variability is small. So you know, if you have good covariates in your model, then hopefully the two methods will not be very different. Angela said that the EBP method, as it is formulated, assumes that you can link your sample and the census. Okay. In reality, the link is difficult to do, so you can't really do, for various reasons, it may not be possible to link the two datasets. And if you don't have the linkage, then ignoring the sample observations and predicting the YIJs, the incomes for the entire population under the model, is what people are doing. The EBP assumes normality of the model error terms. Again, model selection diagnostics is important. A 3-level extension of the EBP that may include also cluster effects in, because that was a point that many users of the ELL were bringing up in various discussions. So a 3-level EBP method is also has been developed by a paper in 2017 that can accommodate cluster and area effects. And conventionally, the EBP method assumes non-informative sampling. So basically, if you want to account for some kind of complex sampling design there is a paper by Maria Godamara with colleagues in Spain in 2018, where they have proposed a method that can bring in survey weights. I suspect the method goes very close to the ideas of Wu and Rao in 2002, and that's a way to bring in this into the EBP formulation. Okay, so and I have these two slides are the same, but I added here the two references in case you want to see the two papers, the two extensions of the EBP method, in case they are of interest to you. Okay. I'm going to stop here. We are already at 11 o'clock your time, 5 o'clock our time, and this is a good point to stop. On Monday, I will start with some applications of the EBP method using the EMDI package, and then I'm going to show you how to fit these models. And then we're going to focus on uses of transformation, which you might find helpful, and how you can do that with R. And then there are some kind of design-based simulations and some empirical results, but you can go quickly through this in order to see how what difference it makes to the estimation. Okay, so I think I'm going to stop here. Angela, do you want to add?
Can I have 2 minutes?
Of course.
Yeah, can I have just 2 minutes? Because there was just another thing that I wanted to mention about the EBP and the ELL, and is that because the ELL doesn't have a random effect that goes at the specific level of the area of interest. So let's say you want to model municipalities. Okay, the EBP has a random effect that goes at the municipality level. The UI has to be municipality because that's you're interested in estimating municipalities. Whereas ELL doesn't have something like that. So in principle, you could formulate, you say this is a 2-level model, area, individual or household, but the area doesn't necessarily have to be the area of interest. It could be something else. And actually, in many applications of ELL, instead of using, for example, municipality, you can see people using something related to the sampling design, like, for example, the cluster. A cluster is not necessarily the area at the level at which you want to get the estimates, but it's another hierarchy. This is why in the last bit that you mentioned, the 3-level model, is because then where is the area playing? So sometimes people say, okay, then I need those two levels, the cluster, let's say, and the area at which I actually want the estimates of interest. So for example, you could have cluster and municipality. Okay, now why ELL is proposed in a way that uses any other geography? Why are they interested in using perhaps a different geography than the geography of interest? And is related to the fact of first not being able to account for the sampling design. So for example, if you have clustered sample, then the idea of formulating the model at the cluster level tells you that at least you're controlling somehow what is happening with the sampling design. You're just not being absolutely completely oblivious to what the sample design is, but you're controlling that. And the second thing is that if you have very good contextual variables, area level covariates at that given level, then maybe you're able to explain most of the between area heterogeneity for that level, which is not the area that you want, but is an area that using a synthetic predictor that doesn't have that extra random effect should be less problematic in a way. So sometimes you're going to see that the applications ELL can be a 2-level model cluster household, whereas the nested error regression model of EBP is the municipality household. They don't have to be exactly at the same level. The reason it's depending on the information that you have, and because the idea with ELL then is to have to be able to explain as much as possible of that between area heterogeneity, so that missing the random effect is the least harmful possible.
Exactly. So exactly, and as I said, if you include in your EBP model in the mixed model that the EBP is using a lot of good information, and you explain the sigma squared U, then perhaps that will lead to similar estimates as the ELL. So
yeah, that's the other thing. That there is, when you see applications of ELL, there is a lot of emphasis about the use of contextual variables, much less in the case of EBP. And why? Because ELL recognizes that they cannot explain that extra between area heterogeneity. So you need contextual variables, you need area level variables to help you reduce that. Whereas on the side of the EBP, because you have that random effect, you think that I'm going to be okay. Now, in reality, if you have that data, just use it. Because much better to have it on the X beta, that you know what you're doing, than to have it on the predicted random effect UI. So it is also important to include contextual variables in the EBP, even if the focus hasn't necessarily been that one.
Absolutely. Okay, I think it's time to stop here. Quite a bit of things to think about, but I'm based on the questions you are asking us, I think that you're thinking how to link the methods to your data, which is a good thing. That's what we want you to think. I mean, I like the questions about, the U hat UI hat. How do you estimate that? This is using the Hayek survey, the UI star, the EI star, and so on. That tells me that you are already translating the methods to data, and I think that's important. Okay. So I know that you're using some machine learning methods, and it will be interesting to see what methods you're using. I don't know if Jose Santiago, I think it's important. If you have any materials that we can have a look into, that might help us also to formulate a bit of discussion next Friday or whenever we organize it, okay? So if you can share something that is not confidential, we will really appreciate that on the methods that you are using. So if you have something on random forests or something else, then please let us know. Other than that, it's good to see you again, and have a good weekend. And we will see you on Monday at 10 o'clock your time, okay, 4 o'clock our time. Angelica, if you can confirm if colleagues can